Hi everyone, and welcome to our first online lecture for this course. I hope everybody is staying safe and healthy at home. And I have a couple quick announcements before we get started. First off, just to reiterate what I posted on Blackboard, exam number 2 is canceled. We're still working on figuring out the proper system to administer the remaining 2 exams, including the final for this course. Haven't quite settled on anything quite yet, but I will let you guys know as soon as we do. Also, just a quick note, our lectures are going to be recorded like this from now on. So for now, I'll be holding office hours, which are optional. You do not have to come to these during the what were originally the scheduled meeting times for our course. I might change that up, move that around a bit if that doesn't work out for people. And I'm also thinking of perhaps setting up a chat room of sorts for office hours. More information on that later. In any case, let's get started with lecture for today. And today we're going to be starting chapter number 5 from the textbook, which covers what are called definite integrals. Okay. So it's been quite a while since we've met, obviously. So at this point, I think the best way to introduce this new chapter is by going back to a recap of sorts that I've tried to keep up with throughout the semester over what I basically view as the 3 parts of this course. And we've completed the first 2 so far. The first of these was basically a bunch of precalculus. And we covered all sorts of different types of functions. So we covered linear functions, we covered exponential functions, logarithms, we covered power functions and polynomials, etc. The second part, which we have just concluded, is on derivatives. What they are, why they're useful, what we can use them for. And we are now going to begin the third section of any calculus course, which covers integrals, what we call integrals. And so how are we going to do this? Well, are going to start with the beginning. And the very first thing that we're going to cover is appropriately going to be section 5.1 from the textbook. Remember, hopefully all of you guys should still be able to access your textbooks online on Wiley+. I'll still be sticking as closely as I can to the material in there. Please remember, you can always check back, not just with these lectures that I'll be posting online, but also check back with the textbook itself. It is still a good resource, and it hopefully is still available to all of you. Regardless, the title of this section in the textbook is Distance and what we call accumulated change. Okay. So the reason we use this, we're starting here, is that one of the more intuitive ways of understanding integration and the notion of definite integrals, just as it was with derivatives, is to look at motion. And when we're talking about the physical idea of motion, we saw that in the case of derivatives, the idea was that if I have a function that gives you distance, you can use derivatives to get a function that gives you speed. And what we're going to be interested in trying to do now is doing the exact opposite. So if I have a function that gives you speed, is there a way to reconstruct the function for the distance? All right, so let's get rid of some of these things up here now. And get to work. Okay. So when it comes to figuring out what distance is, if you already know the speed, there is one formula that hopefully you guys are all familiar with. This is a very basic formula, which is from basic physics. We know that distance is equal to speed times time. Okay, so I think that one of the best ways to introduce the ideas that we're going to be working with for a little bit here is actually to go straight into it's not really an example, but the very first table that they provide in section 5.1, which is something of a thought experiment. So let's say that we have a car that is traveling, and as it is traveling, we are measuring the velocity of this car, the velocity that is displayed on the dashboard, at various different times. So here we're going to have time in seconds, and here we're going to have speed. And we know that at time 0, our speed was 20 feet per second. We know that at time 2, in seconds, our speed was at 30 feet per second. At time 4, our speed was at 38 feet per second. And let's say at time 6, our speed was at 44 feet per second. Okay, and now let's say I ask you guys, how far did the car travel? Alright, if you want to spend some time thinking about this on your own, please feel free at this point to pause the video, give this a little bit of thought. Okay, so how do we go about working through this problem? So one of the key ideas here is that we're going to be using, again, this very basic physics formula. Now, why is this formula going to be helpful here? Well, the main idea that we're going to use in combination with this formula is we can break down the total distance, which is what we are looking for, into parts, each of which we can approximate using our basic physics formula. So specifically, I'm going to break this down into these 3 intervals, and just say that the total distance traveled is going to be equal to the distance traveled between 0 and 2 seconds, plus the distance traveled between 2 and 4 seconds, plus the distance traveled between 4 and 6 seconds. Okay. So this is the main idea of our breakdown. And now for each of these 3 distance components here, we're going to use this distance is equal to speed times time formula. So again, we are going to have the total distance here. And now we're going to have this first component here, which I'm going to show in a blue box. This is going to be equal to the speed. Our speed at the start was 20, times the time elapsed between 0 and 2 seconds is 2. And to this we're going to then add our estimation of the distance traveled between the second and fourth second, which is going to be 30 times, again, 2 seconds have elapsed. And then to this we are going to add, finally, last but not least, our calculation for the distance traveled between 4 and 6 seconds, which is going to be 38 times, again, 2 seconds, which have elapsed. Okay, so if you plug this into a calculator, you'll see that the final answer is going to be 176 feet that have been traveled. Now, I do want to note that this is actually not an equal sign. So again, I want to emphasize that this is going to be an approximation. Just like our first estimates of the value of derivatives were also approximations, this is not going to be exact. And the reason why this is not exact is that these measurements that we have of the speed are given to us at specific moments. So we know that the speed at exactly time 0 was 20, at exactly time 2 was 30, etc. But the speed is going to be changing in between of each of these. So from here to here, our speed changes. And this change is gradual. It's not sudden. And because of this, this 20 here is really just an approximation of what our speed or our average speed is throughout this first interval of time. The same is true for all the other intervals as well. So again, at the end of the day, this is not a perfect estimation of the distance that has been traveled by this car, but it is a pretty good one. And not only is this a pretty good estimation, but this is actually going to be the foundation for our idea of how to calculate integrals more generally. So you'll recall that when we covered derivatives, the basic idea behind calculating the derivatives originally was really to just look at the slopes of lines, right? And just take lines that went through 2 points on the graph that were closer and closer together. Now, the same thing is going to be true for integrals as well. So before I move on to this, and actually, as I like to do in this course in general, I mentioned at the very beginning of this class that there's several different ways of representing functions. And that all of these different ways, tables, as we've just done, functions using formulas for the functions themselves, graphs, all of these are equally valid ways of representing and of considering these functions. And as usual, I like to always, whenever it's possible, try to look at things visually. So let's look at roughly what's going on, graphically speaking, in this example. So in this example, we are told some information about the speed function as, again, a function of time. So we're going to have speed in the vertical axis here, time in the horizontal axis. And we're told that at time 0, we are at a speed of 20. We are told that at time 2, we are at a speed of 30. So let's see, that puts us about here. We are told that at time 4, we are at a speed of 38, which puts us, I guess, about here. And then at time 6, we are at a speed of 44, which puts us about here. Okay, now we can presume, and I'll put this in as a bit of a dotted line, we can presume that the speed itself, the function of speed itself, which we do not know, is a curve that looks something like this. This isn't a straight line. I want to emphasize that this is slowing down over time, as you can see. And you'll note that what we've actually done here in this big formula, let's see, where is it? So in this formula up here, our calculation of the total distance traveled, we actually did 20 times 2. And you'll note that 20 times 2, which we did in blue, is actually exactly the area of this rectangle right here. And 30 times 2 is precisely the area of this green rectangle right here. And 38 times 2 is precisely going to be the area of this yellow rectangle right here. So why am I pointing this out? The reason for this, this is not a coincidence. This is not just something that happened haphazard. It turns out that finding the distance traveled is the same thing as finding the area under the speed curve. Okay, so what I mean by this, when I talk about the area under the speed curve, is that the true answer, again, what we got up here is an approximation. So when we're dealing with all of these, we've added up these three areas. This is an approximation to the true distance that has been traveled in these first 6 seconds. The true value of speed would also add up or include this extra area here that I am drawing in red. Okay, so now I have a question for you guys, and again, you're free, if you want to try to think on this on your own, you're free to pause the video after I've asked this question. My question is, how could we have gotten a better approximation here in this graph? How can we get a better approximation of this true area underneath this curve? Okay, feel free to pause the video. All right. So the answer, if we wanted a better approximation here, there's various different ways that we could do this, but very similar to something that was true for derivatives, is we can use more and thinner rectangles for more accuracy. All right, now obviously that's not possible in this specific example up here. The reason for that being that you actually do not have enough information given in this table for you to be able to do more rectangles. But if you had this full speed function, this entire curve, which I've drawn in as this dotted white line, it would be possible to use more of these by just sampling the curve at more positions. Okay, so let's recap a bit. Board is getting quite filled up, so let's clear this all off. So a quick recap of what we've done so far is that calculating distance say total distance from speed, we saw that this is equivalent to finding the area under the curve. Of the speed. And this idea of area under the curve is basically the equivalent for integrals of the idea of the slope of the tangent line as far as derivatives are concerned. So where derivatives were always giving us the slope of the tangent line, integrals are always going to be giving us the area underneath a curve. Okay, so that's the first point in this recap. And where I want to go with this next is that we can apply this to other non-motion cases as well, which is in general going to lead to this idea of accumulated change. So just like for derivatives, I always encourage you guys to think of the derivative of any function as its quote-unquote speed, even if the function itself didn't represent distance traveled. So in the same vein, when we think about integrals or definite integrals, the idea is always going to be similar to the idea of calculating total distance traveled if you're starting off from speed, right? You're always talking about some accumulated total change that you're measuring. And graphically speaking, let's just draw a graph with some arbitrary curve here. The idea is always going to be that we're going to approximate the area underneath this curve by sampling the curve at some finite number of points and adding up the areas of all of these rectangles that I am drawing here. So if you add up the areas of all these rectangles in red, this gives you a decent approximation to the true area underneath this curve, which I have put here in blue. Okay. Now this is actually something interesting in its own right. And I do want to discuss this for just a little bit, which is just to mention that this question of finding the area underneath a curve, wrong color there. Let's switch. So I just want to make a note here. So finding the area under a curve is actually hard. And the reason for this is that we have no geometry formulas for this. So it turns out that from a geometrical perspective, the idea that we have with all these rectangles is also a very straightforward approximation idea of, instead, rectangles are easy, right? We know that their area is equal to width times length. So what we're really doing here is we're approximating a complex shape by using simple rectangles. Okay. So I'm going to get into now a couple things, I guess, that sort of go beyond the scope of section 5.1, but just to sort of close off the lecture for today. Some of this is basically from 5.2, and there is some stuff from other sections as well. I'm condensing some information here. But here I want to just define the idea of the definite integral and the notation that we use for this. So let's suppose that f of x is continuous between the points x equals a and x equals b. Then we define the definite integral of the function of f of x from a to b, which we denote with this symbol here. This symbol is called an integrand. And down here at the bottom of the symbol, we're going to write a little a. This is the starting point. And at the top, we're going to write a b, which is the end point. And we do this of f of x dx. So you'll recall when we did derivatives, this dx here, this is basically the same dx in what we wrote as dy dx. So this dx down here and this dx up here, these are the same. Okay, so this is just notation, but what is this definite integral? This is the area under the curve of f of x between x equals a and x equals b. Cool. All right, so just a couple final notes about this before I finish up. First, units. The units of the definite integral are the product, which means you're multiplying, of the units on the horizontal and vertical axes. So, for example, in the case that we covered involving the car, so we mentioned that in the case of distance, distance is obviously measured in feet, but note that feet itself, the unit of feet, is equal to the unit of speed, which is feet per second, times the unit of time, which is second. So if this is distance, this is the unit of speed, and this is the unit of time. So just like in this case, this is how you get the units for distance. Similarly, in any case where we're doing a definite integral, if you're asking yourself, what are going to be the units of this measurement of the definite integral, well, it's going to be the product of the units that you're using on the horizontal and on the vertical axes. Okay. So that's the first note I wanted to make. But there's a second note that I want to make, which is that for now, we approximate. I'm going to start abbreviating the definite integral as def int with those sums of rectangles. And this is very similar to the way that we approximated the value of the derivative early on by taking the slopes of lines that went through 2 points, getting perhaps closer and closer together. But very soon, in fact probably next lecture, we will have integration rules. which we can use as shortcuts. Again, just like we did with derivatives, we had all these rules for derivatives. And yes, there's a lot of them to learn, and yes, it's not necessarily easy, but it's a lot better, it's much faster, actually, to use those rules than to try to constantly approximate all those derivatives by hand. Well, the same is going to be true for integrals. We're going to have a set of rules for those as well. Don't worry, there are all those ideas of product, quotient, chain rule, that kind of advanced rule. We're not going to get there in this course. We're just going to cover very basic rules for integration. But there's going to be rules for these as well, and that's sort of going to round out the rest of this course from now on. Okay, so that's pretty much all I have for you guys in today's lecture. As always, feel free to shoot me an email if you have any questions. Drop by office hours later tonight. I'll post all the instructions for that on Blackboard, so all of you guys know where to go. Again, office hours, all of that is totally optional. I recognize that what with the strange circumstances we're in now, it might not be possible at all to even find a time where all of you guys, all of us, can even meet regularly. So with that said, the last thing I want to mention is that I recognize with our sort of strange circumstances that a lot of the resources that would usually be available to you guys to help you guys study or help you guys get any sort of assistance with this course are maybe not available to you guys anymore. So what I want to mention is that I think this software that I'm using here to lecture is pretty good, but I think it actually is a fantastic tool for demonstrating any specific problems or to work through any problems. So I want to just mention that I will be more than happy to use this to post or make relatively short videos I can post on Blackboard, demonstrating the methods of working through any problems or any sort of example problems for the homework set or any other assignments. So if any of you guys have any problems on the homework that I assign that you're struggling with, or you'd like to see how to work through the problems themselves, just let me know. I'd be more than happy to quickly work up a video on this software showing you how to work through these and just posting that on Blackboard so everybody can see that and refer back to it as you need to as you're working through these assignments. Alright, that's all I have for you guys today, and I'll see you guys later today.